Let me remind you that we have a problem session at 2:30. If you have some problems that you would like to share, please contact me. And so we will resume at 2:30 after lunch. So now we go with the fourth lecture of the series by Isabel Cortez. Thank you very much.
Okay, thank you. Okay, today I'm going to talk about the relation between full groups and orbit equivalence. And full groups were introduced in the mini course of Bolodia, but I'm going to recall the definition just to use the same notation here. And I'm going to work always with the Cantor system at the beginning for a group action. So suppose that we have a Cantor system. In general, I'm going to work with free and minimal Cantor system, but sometimes it's not necessary. So the full group will be the group of the homomorphism on X such that the orbit of F for any point is included in the orbit of the action. This is the big full group. And the topological full group, one way to define the topological full group is the following. So you take, for example, the function, call this phi, the function from the full group product with the space X to the group G, that take upper Fx and will give you D, where D is just the time of the orbit of X where Fx arrives. And the topological full group is the subgroup of the element of the full group. Where the restriction of this function, when we fix the first coordinate with F, when this function is continuous. And this is the same to say that this is the set of the subgroup of all the elements of the full group for which there exists a finite closed partition of X and for every element of the partition, an element of the group. Such that the restriction of F to the element AI is equal to the action of the element GI. So this is the topological full group. And the first thing that we see, okay, if the space is not totally disconnected, for example, if the space is connected, this thing is trivial. This will be isomorphic to the group. So this is the first thing that you can see also. The group, you can always identify the group G, the group which is acting, with a subgroup of T, of the full group, the topological full group. And If the space if the space X is connected, this is an equality. So in that case, the topological full group is trivial. And before to try to explain what is the relation with this group and orbit equivalence, I would like to show you how can we compute for an example this group. In general, yesterday we defined the dimension group for a minimal Cantor system. And the dimension group, in some sense, is very easy to compute because you take the Bratteli diagram and you define the dimension group as a direct limit. Here it's not the case. This group is more complicated. It's not easy to say, okay, the full group of such system is like that. But for some example, this is easy to compute and you can say something about the system. So just to try to see what kind of element we have here, I'm going to show you the full group of the odometer. And I'm going to work with the odometer given by a C action, but you can do exactly the same for an odometer given by a more general group action. Okay, suppose that we have an odometer given by a C action. So for that, we need an increasing sequence of a positive number. And the odometer, remember that it's just the inverse limit. The inverse limit defined by the projection of this group to this one. And the transformation is just add one coordinate by coordinate. And for this system, we can construct a very special sequence of Kakutani-Rocklin partition. So suppose that I fix n. And for n, I'm going to define the set Cn of all the elements of the inverse limit. Where the coordinate n is the class of 0 in the CPNZ. I don't know, I'm going to write this like, I don't know, like this. And what happened when I apply T to this set? I obtain the set of the element of X, where Xn is the class of 1, and so on. So at the end, we are going to have the following partition. This is a Klopen partition of X. And if I do the same for n plus 1, Pn plus 1 will be finer than this. And we get a sequence of Kakutani-Rocklin partition. So in that case, we have, if you remember, when we define Kakutani-Rocklin partition, we talk about towers. So here, for Pn, we have just one tower. So this is like this. This is how the partition, this is the only tower of the partition Pn. So what happens if I take an element of the topological full group? Okay, I'm going to right here. Okay, suppose that we take an element of the topological full group. Remember that the sequence of partition Pn generate the topology. And these elements have the property that locally they look as the action of some element of the group. So there exists an N such that F on every atom of the partition Pn is the action of some element of the group. So there exists N such that for every element of the partition Pn, there exists some element of the group such that F, the restriction of F to this element of the partition is equal to the action of this element of the group. So if we call the element of the full group that satisfy this property Tn, these are the elements of the full group that verify this. We have that the full group, the topological full group, will be the union of this. And this is an increasing union. So something which is the action of an element of the group on every element of the partition Pn will have the same property for the element of the partition Pn plus 1. So this is an increasing union. And until here, you can do exactly the same for every minimal Cantor system given by a C action. But the particular property for the odometer is that this set, the set Tn, is a subgroup. When you do the same for more general minimal Cantor systems which are not odometer, minimal Cantor system having more than one tower at every level, you can say that this is a subgroup. So in the case of the odometer, this is a subgroup. And how can we, and we can describe this. And for that, we need to see what happened with the tower when we apply an element of the topological full group. So now I'm going to make a picture here. And I'm going to see what happened with the element of the level of the tower. So what happened if we apply f, this function f, to this atom of the partition? So if we apply f to an element in this atom of the partition, we have that fx is equal to Tijx, and this belongs to Taj plus Jcn. So we move the atom of the partition. And the dynamic here is like this, it's very simple. So when you are here, you go to the next step and so on, and then you come back, and so on. So to see what happened, we need to write this we need to write this in the following way. So we know that this is equal to some, that I'm going to write this like a permutation, some number plus another one. I'm going to explain what is this, where this is something which is in between 0 and Pn minus 1. And this is something which is in Pnz. So what happened with this atom of the tower when we apply the function f? So we move this atom to the atom T, this thing, Cn. And this number here will tell us how many times you have to do this. So when you have an element of the topological field group of the odometer, you can identify this element with this permutation, and with this element, if I take this for every j, with an element in Pnc power Pn. So we have that an element of we take f, we can identify f with something which is a pair in, write this like this, in Pnc power Pn, product with the permutations in of permutation for Pn element. If we know these two things, we know f. But now we need to see what happens if we compose two elements. So what happens now if I take another element, and I'm going to write like this. What happens when we do the composition of this? What happens when we do the composition of these two things? Without make computation, it's easy to see if we make the composition of these two things, we get something which is always in Tn. If you have more than one tower, this is not true anymore. Because things where they arrive to the top of the tower, then they split and we don't know where. But in this case, this composition is in Tn. And we can write explicitly. So if we compute this, so we get the same thing that I did there. So this is T, and I'm going to write Ag like this. X. And then here I'm applying G in an element which is in T sigma F J Cn. So I get T sigma J sigma F J, I don't know, plus maybe C J. Here is sigma Fj minus sigma Fj and plus this thing. And here we get, from this we get that the composition of this, we can identify the composition with the pair. I'm going to write here before, it's easier, with the composition of the permutations. And here we have something which is not exactly an addition of two vectors. So we have to permute the coordinates of the vector corresponding to G plus the vector corresponding to F. So we get something like this. J sigma F J, oops. J sigma F J, a vector, plus the vector corresponding to F. So here we need to compose the two permutations, but here we take the vector CF corresponding to the function F, the vector that tells you how many tours you have to do, and we add to some permutation with the coordinate of the vector corresponding to G. So what does it mean here? With this, we have that the group Tn is isomorphic to a semi-direct product of Pn C power Pn with the permutations of Pn elements. This is Tn. And because we know that these are contained, so this is the group Tn is contained in the group Tn plus 1, we get that the dimension group, the topological field group of the odometer will be isomorphic to a direct limit of these things. Some direct limit, I don't know. So the dimension group of the odometer, we can express the dimension group of the odometer as a direct limit of these groups. And if we work with odometers given by more general group actions, we can do the same because we have something similar to Kakutani-Roglin partition in that case. And in the general case, so when G is residually finite, when G is residually finite and we have an odometer which is given by a sequence of finite index subgroups, normal, the odometer given by this sequence will have also a dimension, a topological field group, which is also isomorphic to the direct limit of exactly the same. So here we will have and here's something, the function that defines the direct limit. So for the odometer, we can express the topological field group as a direct limit of something. And here, maybe the first conclusion that we can say about this group, what happens if the group G is amenable, for example? If the group G is amenable, okay, this is always amenable, the permutation thing. If the group G is amenable, Gn is amenable, this is amenable, direct product, direct limit of amenable group is amenable. So we get that if G is amenable, for the odometer. This is just true for the odometer. In the odometer case, G is amenable if and only if the topological field group is amenable. So for the odometer, we can say something very explicit. And this gives you an idea, more or less, how are the elements of the full group. So there are things that make some permutations and something which is like a translation. In general, it's not easy to compute a topological full group like this. So now, what is the relation of this group, of the topological field group and the field group with orbit equivalence? Okay, remember that orbit equivalence to systems are orbit equivalent if there is an homeomorphism that sends the orbits from one system to the orbit of the other one. And when the systems are free, which is the case that we are assuming here, when the systems are free, we can define something similar that we did yesterday for C actions. So when the systems are free, we can define the function from G product X to gamma, the function that take a pair Gx and give you some gamma, where gamma is exactly the place of the orbit of Hx where Tjx arrive. So this is where Tjx is equal to S gamma Hx. There is another thing that I didn't say yesterday when you are not working with the, for example, if you are working with connected spaces, if X or Y are connected, this notion of orbit equivalence is trivial. It's equivalent to isomorphism. So when you are in the case of connected space, all these notions are the same to isomorphism. Okay, and when we have this, there is a notion okay, when we have this function f, we say that the systems are continuous orbit equivalent the systems are continuous orbit equivalent if for every j, the function that fixes j in the first coordinate from x to gamma is continuous. And remember yesterday when we defined strong orbit equivalence, we defined some function alpha and beta. The function alpha is the same function here for d equal to 1. So what is the relation? Now I can tell you the relation with the full group and orbit equivalent. Here I have to say this was shown for C actions. The thing that I'm going to write here was shown by C actions by Giordano, Putman, and Scow. '99, I think. And for more general group actions, Medinet. Oh, I don't remember, 2011, I think. And the theorem tells, okay, two systems have the same full group if and only if they are orbit equivalent. And they have the same topological full group if and only if they are continuous orbit equivalent. And there is, I have to say, a comment about the special case when G is equal to gamma and this is equal to Z. When we are working with C actions, continuous orbit equivalent is equivalent to B flip conjugate. So this is a result from Mike Boyle. In that case, continuous orbit equivalent is equivalent to flip conjugacy. Remember that flip conjugacy is the first system is conjugate, xt is conjugate to S or S minus 1. And when we have this, we can write this in another way. That I can write flip conjugacy. I'm going to write flip conjugacy in another way. Flip conjugacy is the same, in that case, to say that there exists an isomorphism between the integers and the integers, and an isomorphism, H, from X from the first system to the second one, such that the diagram that I'm going to write here commutes. H, H. This is a very strange way to write flip conjugacy. It's the same. Why? Because this is an isomorphism. The only isomorphism that you can have here is the identity or minus the identity. So this is another way to say that T is conjugate to ys or conjugate to ys minus 1. And continuous orbit equivalence in the case of C action is equivalent to this. And what happened for other group action? The question that we can ask is, okay, is continuous orbit equivalence equivalent to the same? But here, instead to have Z and C, having G and gamma? And the answer is no, this is not true for C2 actions. And so this notion, when I'm going to write here the notion of isomorphism of systems. We say that the two systems are isomorphism if there exists an isomorphism of the groups. And anomion such that we have the following, the same diagram. So flip conjugacy is this for D and gamma equal to Z. So the question is, okay, continuous orbit equivalence is equivalent to this, and this, the answer is no. For C2 actions, there are odometers. There are C2 odometers which are continuous orbit equivalent, but they are not isomorphic. They are not ladies. And this is a consequence of a result. I'm going to write here. This is a result with Medinet. For odometers, or minimal equicontinuous free systems. For odometers being continuous orbit equivalent, is equivalent to have the following. It's equivalent to have a sequence of groups is equivalent to have a representation of both systems Okay, remember that the odometers are always represented using finite index subgroups. So to be continuous orbit equivalent for odometers is equivalent to have a representation Gn for the first one, a representation gamma n for the second one, such that there is an isomorphism between there exists an isomorphism between G0 to gamma 0 such that send the group Gn to gamma m and such that the index of G0 is equal to the index of gamma 0. This is very rigid, but in C2, Using this, it's easy to construct odometers with this property, which are not isomorphic. And the problem is when you have an isomorphism between finite index of groups in C2, sometimes you can't extend this to C2. This is more or less the idea why we can construct examples of things which are continuous orbit equivalent without being isomorphic. In dynamical terms, this is equivalent to say, more or less, that in the first system, you have a Klopen set. In the second system, you have another Klopen set. Why? Such that the group G0 acts on C0. That means that the set of return times to this Klopen set is the subgroup G0. And here you have the same for gamma 0. And the restriction of the action, these actions are isomorphic. So for odometers, continuous orbit equivalence is equivalent to have an isomorphism, but for subsystems, which are not exactly the system, but they are not so far from being the system. And at the same time that we were working with Medinet, there is another. Yes. And another work which appear at the same time, more or less, is give you another kind of rigidity result about continuous orbit equivalence. This is from, I don't remember the name. It's something, I have to read this. This is Chin Lee. So another question, for example, is to know, okay, what happens if I have two systems which are continuous orbit equivalent? One system is given by the action of a group G, the other one is given by the action of a group gamma. There is some restriction in gamma and G, and here there is an answer. If G and gamma or gamma are finitely generated, they have actions which are continuous orbit equivalent. If they have actions which are continuous orbit equivalent, then they are, the groups are quasi-isometric. So this is a restriction in terms of the groups. So there is some relation in the groups. So there is some restriction on the group to have systems which are continuous orbit equivalent. Yes. Yeah. Yeah, I think this is in the concept of reactions. Yeah. And these actions are free also. But for example, the result of Medinet, so the equivalence of orbit equivalent if and only if you have the same full groups or continuous orbit equivalent if and only if you have the same topological full group. This is more general. This is not necessarily for minimal system and free system. It's more general than this. Yeah, in that, yeah. Yeah, okay. Yeah, for the definition, you're right. Yeah, then I'm not sure if I'm saying something which is correct there. I need to check the hypothesis of Medinet, but I think there is something general there. It's not just for minimal free actions. Mm-hmm. Yeah, but I have to check the hypothesis for that. And what else? Okay. Just to say something about the tools in the proof of Medinet for this equivalence. Maybe the key tool that he used there is the following thing. So when you have an isomorphism between the topological full group or between the full group, isomorphism, this is always spatially defined. So that means that there exists some omeo from the spaces such that these things give you that diagram that commutes. In the topological full group or the full group if you are working with the full group. This is the key tool to show this result. And just to finish, I talk here about, start talking about Bratteli diagrams, then about some invariant dimension groups, and now about some relation with orbit equivalence and full groups. There are more things that you can say. For example, I'm just going to mention, because I don't have time, but there is more invariant, more algebraic invariant that you can associate to minimal Cantor systems, or Cantor system in general. So another group that you can associate to this system is the group of automorphism, which was defined in the talks of Michael and Mike. And there are some results about the group of automorphism related to minimal Cantor system. And there are a lot of people working there, so you can look for this. For example, there are some results from Brian Accra, Van Seer. There are also from Durand and Donoso, I don't know, Mas, Petit. There are more people working there. And the result studying properties of this group are related in the case of subshift with the complexity of subshift in general. So for example, subshift with low complexity means that the length of words, the number of words of length nth, for example, grows in a linear way. So for that case of properties, you can find some relations in the properties of the group of automorphism. And there are a lot of things that you can say here. But I don't have time to talk about this. So, okay. Another thing. I wrote some notes. The notes are in my web page. In this note, I have all the reference. So if you want to look for more information and the proof and all of this. Okay, thank you.